I mean, that's basically the whole pattern, but we can try it some more till we get a feel for it. Let's look at a third example. So here we have the indefinite integral of x times natural log of x. And now I need to think about which of these I want to be a and which of these I want to be db. So let's look. If we tried a equals x, okay, I know how to find dA, but if I tried to let db equals natural log of x, natural log off the top, and the goal here is to get us an integral that's simpler. So if I can't do, if I couldn't find the indefinite integral of natural log, there's really no hope. So the way that we're going to try to do it is we're going to try a equals natural log x and db equals x, because I can find then that b is equal to 1/2 x squared, and I know that dA is equal to 1 over x. So now I'm just going to take these pieces. Remember that it's going to be ab, which is going to be natural log of x times 1/2 x squared minus the indefinite integral of dA times b. We always end with the dab. So dA times b, which is 1 over x times 1/2 x squared dx. And now this is really cool because I'm going to see some cancellation. If I think about 1 over x times 1/2 x squared, I can cancel that x with that x. And this will simplify to the natural log of x, 1/2 natural log of x times x squared minus, and I can pull that 1/2 out front, and I'm just left with x here, which means that I have 1/2 natural log x. I would actually write x squared in front here, minus 1/2. The antiderivative of x is 1/2 x squared c. So I'm going to look at 1/2 x squared natural log x minus 1/4 x squared plus c. Now let's look at the antiderivative of x squared times sine of x dx, which will be, okay, let's see. What do I want here? I definitely want a to be x squared, and I want my db to be sine of x. And the reason is that, let's go forward and look at this. So dA is equal to 2x, and b is equal to negative cosine of x. So if I do this as a times b, x squared times negative cosine of x minus 2x times negative cosine of x, and I'm always ending on that dab, dab. This 2x is a little bit better than this x squared. If I had tried it the other way, I would have had x, if I had tried x squared equals db, I would have had 1/3 x cubed here times a trig function, and that's worse. So the goal here is that our dab integral is at least a little bit better than our initial integral. And we're trading one integral for another, and our hope is that the new integral is simpler. So going from here, we just keep this as negative x squared cosine x, and then we're can do the minus minus, and we get plus, we get 2x cosine of x dx. Looking at this 2x times cosine x is not something I know how to do automatically, and in fact, I'm going to have to use IBP again. So let's do this over here as a side calculation. Some people have different tricks for doing this. I just like to pull it out, take it seriously, make it be its own thing, and then work from there. So here again, I'm going to let a be 2x and db equal cosine of x. So that means the derivative of a is 2, and the antiderivative of b is sine of x. So this integral would become a times b, which is 2x times sine of x, minus the integral of 2 sine of x, and the integral of 2 sine of x is 2 times negative cosine of x. So this would be 2x times sine of x minus 2 times negative cosine of x plus c, and the minus minus becomes plus, so this is 2x sine of x plus 2 cosine of x plus c. The entire thing was a side calculation of trying to get this to a place where I could plug it back in here. So taking this entire expression, which required its own side calculation, I end up with negative x squared cosine of x plus 2x sine of x plus 2 cosine of x plus c. So the moral of this story is sometimes you have to do integration by parts more than once. It may be that you're doing an integration by parts and then this pops up, and after you simplify it, like, wait a minute, this integral still requires integration by parts.